Hello everyone and welcome to this course on ontology knowledge management. I'm excited to have you here whether you are a data engineer, software developer or AI practitioners. Someone who is curious about semantic technologies, then this course is designed to help you understand how ontologies can perform the way organizations manage and use the knowledge. My name is Suchismita Sahu. I have been working in the fields of AI, artificial intelligence, knowledge engineering, and semantic technologies. In this course, I will share both the theoretical foundations and practical insights I have gained while building ontology-driven systems. Throughout this course, I will guide you step by step through the concepts, standards, and practical techniques used in building ontology-driven systems. Before we dive into technical details, let's take a moment to understand why this topic is important. Today, organizations generate massive amounts of data. However, data alone is not enough. To derive meaningful insights, systems need context, relationships, shared understanding. There is where ontology comes into the picture. Ontologies and knowledge graphs become very powerful. They enable machines to understand information in a way that supports search, reasoning, and interoperability. In this course, we will start with the foundations of knowledge representation and gradually move toward more advanced concepts used in real-world semantic systems. Throughout this course, we will cover the fundamentals of knowledge representations and semantic structures, RDF data model and how information is represented as triples, different RDF means here resource definition framework serialization formats such as Turtle, JSON-D, LD, RDF, XML, etc. RDF schema and how it helps organize knowledge through classes and hierarchies. The wave ontology language in short form OWL, which enables the logical reasoning over data. SPARQL, that is the query language used to retrieve and manipulate semantic data. SKOS and taxonomy management for organizing concepts and vocabularies. The complete ontology development lifecycle from requirements gathering to deployment, the various types of ontology design patterns and best practices for creating reusable semantic models and real-world applications and the impact that semantic technologies can have within enterprises. So, by the end of this course, you will have a strong understanding of ontology engineering principles and the confidence to begin designing and working with semantic models in practical environments. So if you are ready, let's begin our journey into the fascinating world of ontologies and the knowledge management. You don't need to be an expert to get started. Welcome to the course and let's get started. So module 1, we are going to cover the foundation of knowledge, that is the knowledge representations. Knowledge representation, in short form this is known as KR, focuses on expressing information in a form that enables machines to reason about it. It provides the foundation for intelligent systems by transforming human understanding into structured models. So declarative knowledge that represents facts, observations, describes what is true about the world. Example, Paris is the capital of France. And here in the semantic structures that bridge the semantic systems that bridge the gap between human meaning and the machine interpretation through formal structures and relationships. So procedural knowledge we are going to cover represents actions, rules, how tasks should be performed, etc. Second, coming to the RDF data model. RDF means Resource Description Framework. Is the standard model for representing information as a graph of interconnected resources. RDF expresses knowledge using triplets, each consists of subject, predicate, and object. The module 3 we are going to discuss and learn about the serialization formats. The RDF data can be represented in several serialization formats and each optimized for different use cases. For example, turtle, that is .ttl with extension .ttl file, that is human readable syntax for RDF, preferred for ontology development and debugging, concise and easy to maintain. JSON-LD, the JSON-based representation of linked data, familiar to web developers, bridges traditional web applications and semantic technologies. RDF/XML, that is XML-based RDF serialization format, widely adopted in enterprise environments, more verbose and complex for manual editing. So don't get bothered about that. I am just showing one piece of slide with the module name, and inside that I am telling so many things. So don't get bothered about this. I will be covering everything. I am just giving you what we are going to cover in each module. And also I will be sharing the slides and the knowledge training materials in the form of some docs, in the form of some turtle files. I'll be sharing all these resources with you. So the next module is about RDF schema. RDF schema extends RDF by introducing vocabulary for defining classes and hierarchies. So RDFs add structure and meaning to RDF graphs through taxonomy relationship. Key concepts include RDFS class, RDFS subclass of. Subclass means defines categories or types of entities, and subclass means establish hierarchical relationship between different classes. RDFS domain specifies the expected subject class for a property. RDFS range specifies the expected object class for a property. So what is this subject class? What is property? What is object class? That we are going to learn next. I am just giving you the introduction. In next module, we are going to learn about web ontology language, and that enhances the RDF and RDFS by introducing richer semantics and logical expressiveness. OWL enables automated reasoning, allowing systems to infer new knowledge that has not been explicitly stated. OWL capabilities include defining disjoint classes, applying cardinality restrictions, modeling complex relationships and constraints. The next is about SPARQL querying. So SPARQL is the standard query language for RDF data and semantic graphs. Common query types include select queries, construct queries and ask queries. Select queries includes retrieve matching data from RDF datasets. Construct means generate new RDF graphs from existing data, and ask means return true or false answers. Next is about SKOS taxonomy, that is simple knowledge organization system, is designed to represent controlled vocabularies, taxonomies and thesaurus. So concept management supports, SKOS supports hierarchical structures using relationships such as broader concepts, narrower concepts and related concepts. Labeling standards, SKOS enables multilingual terminology management through standardized labels including preferred level, alt level, etc. Next is the very important part, that is the ontology design patterns, and it provides reusable modeling solutions for common semantic challenges. Few design patterns include the content patterns, and that addresses domain-specific representation needs. Examples like modeling time, events and locations. Logical patterns improve reasoning effectiveness, representing n-ary, tertiary like 3, n-ary relationships. Alignment patterns enhances interoperability across systems. For example, mapping internal concepts to schema. Then reification patterns that enables metadata about relationships themselves. Recording, for example, recording confidence scores or provenance informations, all this. module is ontology lifecycle, where we will be discussing structured lifecycle that includes the requirement gathering, where we have to define the business objectives, identify stakeholders and use cases, and determine the domain scope. Second is modeling, develop classes, properties, and constraints. Third is create ontology artifacts using tools, that is open source tool Protégé. Testing means validate consistency and completeness, execute reasoning processes to identify modeling issues. Deployment means publish the ontology within graph databases or triple stores. Integrate semantic assets into operational environments. So next one is about semantic impact metrics. So why we are studying about this semantic analysis, semantic knowledge. So organizations implementing semantic technologies often observe measurable improvements in information retrieval effectiveness. So those benefits includes like reduced occurrences of null search results, enhanced synonym recognition, improved concept expansion, greater contextual understanding of user intents, etc. So let's start our session with the module 1. Hello everyone, welcome to this course. Myself Suchimita Sahu, the instructor of this course. The prerequisite of this course is to learn the complete domain model using Protégé tool, how to build using Protégé tool, and relationship, what are the different kinds of classes, object, data properties, annotations, individual, how to using those, how to build the complete ontology system and querying those different kinds of relationship through this SPARQL query. This is the subsequent follow-up of my course part 1, that is building healthcare ontology systems with Protégé, OWL, RDFS, Apache Jena, Husky, for SPARQL languages. So without that, if you don't have any prior knowledge about all these, then it will be difficult for you to understand this specific course, that is building an agentic ontology-based agentic AI system from natural language to intelligent semantic reasoning. So let's start. I'm really excited to have you here because throughout this course, we are not going to build another chatbot. We are not going to build another retrieval augment generation or RAG application. We are not even going to build a simple AI agent. Instead, we are going to build something that closely resembles how enterprise AI systems are designed today. By end of this course, we will understand how to design an ontology-driven, knowledge graph powered agentic AI platform capable of answering complex domain specific questions while maintaining accuracy, explainability, and scalability. Everything you will learn in this course is based on a real project that I have designed and implemented from scratch, and this is not a toy example. This is a production style architecture that combines semantic technologies, knowledge graph, modern APIs, and large language models into one agentic platform. That is intelligent platform. Throughout this course, I will explain not only what I built, but also why I built in this way. Because the why is much important than the code itself. And yes, there are some gaps. Each and every lecture, I will give you some assignment to incorporate, to address those gaps which purposefully I have kept in this project. So that at the end of this session, we will be master into building this enterprise ontology based agentic AI system that is based on the healthcare domain. So let's start. Let's begin with a question. If someone asks an AI assistant, show me all diabetic patients admitted to the ICU who received insulin during the last 7 days and whose HbA1c is above 8. So can a normal chatbot answer this? Probably not. Can a traditional SQL database answer it? Possibly, but the user does not know SQL. Can a simple RAG application answer it? Again, probably not. RAG works by retrieving documents. It searches chunks of text. It does not understand relationships. It cannot naturally reason over concepts like patient, admission, diagnosis, treatment, medication, laboratory, all these, right? These are relationships. Healthcare is fundamentally rational. The same challenge exists in other domains like finance, manufacturing, supply chain, cybersecurity, scientific research. All these domains are highly interconnected, and this is why we need semantic technologies. Instead of storing information as disconnected documents, we represent knowledge as connected entities. Once information becomes connected, AI can reason over those relationships. That is the motivation behind this project. Let's look at how AI systems have evolved. The first generation of AI applications relied purely on machine learning. They performed classification, predictions, clustering. They worked well for structured numerical data. The second generation introduced large language models. Now machines could understand and generate human language. However, LLMs have a significant limitation. They only know what they learned during training. They do not know why organizations have data. To solve this, RAG becomes popular. Instead of relying only on a model memory, RAG retrieves relevant documents from an external knowledge base. This improved the factual accuracy, but another problem remained. RAG retrieves text. It does not retrieve meaning. It cannot naturally understand relationship between entities. For example, it may retrieve a paragraph mentioning patient, doctor, medication, diagnosis, but it does not inherently understand that doctor diagnosed patient, treatment produced prescriptions, like the relationship between different entities, extracted entities, right? And those relationships exist only implicitly inside the text. And that is where knowledge graphs becomes important. Knowledge graphs explicitly represent relationships. And once we combine knowledge graphs with LLMs, we obtain systems capable of semantic reasoning. But we can go one step further. Instead of asking a single LLM to perform everything, we divide responsibilities among multiple intelligent components. Those components becomes AI agents, and this leads to us to agentic AI system. However, building agentic AI system is the scope of next part of this complete course series. In this part, that is part 2, we will be able to know ontology based knowledge graph assistant. So let's understand the three major building blocks of this project. The first building block is the ontology. The ontology defines the vocabulary of the domain. It answers questions like what entities exist, how are they related, what constraints apply, what does the diagnosis mean, what is a treatment, what is an appointment, what's a medication, what is a laboratory test, right? Everything begins with the ontology. The second building block is the knowledge graph. The ontology defines schema. The knowledge graph stores the actual data. Knowledge graph is the instance of the ontology. For example, if I say that patient John visited Dr. Smith on a particular date, received a diagnosis with prescribed medication, and underwent laboratory testing. Those facts becomes nodes and relationships inside the graph, and the third building block is the AI agent. Instead of manually writing graph queries, users simply ask questions in natural language. The AI agent understands the user's intent, identifies the relevant ontology concepts, generates the appropriate graph theory, executes it, validates the response, and finally produces a human readable answer. The user never needs to know cipher. The user never needs to know SPARQL. The complexity remains hidden behind the AI agent. This is exactly what modern enterprise AI systems aim to achieve. So here, it's a very common question. Why did not I simply use a vector database? The answer is very simple. The vector databases are excellent for semantic similarity. Knowledge graphs are excellent for relationships. They solve different problems. Suppose someone asks that which patients were treated by doctors working in the cardiology department. A graph database can answer this naturally because it traverses relationships. Suppose someone asks which medications are prescribed by hypertension. Suppose someone asks which medications are prescribed for hypertension. Again, relationship matters here. Suppose someone asks find all patients who received medications they are allergic to. Now, multiple relationships must be combined. This is difficult for document retrieval alone. Graphs excel at these problems. The ontology provides meaning. The graph provides relationships. The LLM provides natural language understanding, and all together they create an intelligent reasoning system. So now let's add the overall architecture. So imagine the complete system as several layers. At the very top, we have the user. The user interacts using natural language. They request, the request enters our first API endpoint. Then it goes to the first API backend. The backend performs some kind of authentication, right? Then validation, logging, request processing. The request is then sent to the AI orchestration layer. This layer contains multiple logical responsibilities. First, the user's intent is analyzed. Next, the ontology is consulted to identify the relevant domain concepts. Based on these concepts, the system determines whether the query should be translated to cipher, SPARQL, or any other internal operations. Once the query is generated, it passes through the validation. The validation layer ensures that the generated query is syntactically correct and aligned with the ontology. After validation, the query is executed against the knowledge graph. The graph database returns the structured results, and those results are then transformed into human-friendly explanation. Finally, the response is returned through the API to the user. Although this appears to be a single AI assistant, internally multiple components cooperate to produce a reliable answer. And this layered architecture is significantly more robust than asking a language model to generate answers directly. So here this slide contains the responsibilities of each layer that we discussed few minutes back. So why we will learn this course? Over the next lectures, we will gradually build every component of this system. We will begin by exploring the project structure. You will understand why every folder exists, why every module has been separated, how maintainability was considered from the beginning. Then we will move into ontology engineering. We will learn how to design an ontology using Protégé that we have already discovered in our part 1 session. Here what we will be using? We will be using that ontology built with the Protégé and convert that into the knowledge graph. We will convert the ontology into a knowledge graph. Okay. So we have already discussed RDFS, SHACL we need to still discuss about in this part 2. SPARQL we have discussed, we need to yet discuss about Cypher, Neo4j, and after that we will build the backend APIs. You will see how scalability, observability, authentication, logging, rate limiting, validation and deployment have all been designed for production environments. Finally, we will study the biggest challenges encountered during development, why those challenges occurred and how they were solved. My goal is not just to teach the project, my goal is to teach you how enterprise AI systems are engineered. So before we move to the next lecture, remember one key idea. Artificial intelligence is no longer just about language models. The future belongs to systems that combine multiple technologies. Large language models, knowledge graphs, ontologies, reasoning, semantic search, production APIs, observability, scalable deployments. When all these components work together, we move from simple conversational AI to intelligent enterprise systems. So, in this part 2, we are going to discuss about the architecture of simple conversational AI using all these technologies. Why this is simple conversational AI instead of intelligent enterprise system? Because I want to show you, I want to demonstrate you from how we have continuously evolved our application. It is not like that the world is going behind the agentic AI system, so drastically we have to move to that step, jump to that step without analyzing, without experiencing a simple conversational AI. Once you build a simple conversational AI, it will be easy to understand what are the shortcomings present inside that, and so that you should be able to move to the next milestone, that is your next roadmap, that is your next technology stack, technology strategy. Platform, a case study that we have considered about the healthcare. So prerequisite of this course is to understand the how we have, this is the part 3 of this complete one bundle, the course bundle, that is to building multi-agent AI systems based on ontology. So in part 1, we built the ontology, healthcare ontology, and then we, with the help of tool Protégé, then we had built also RDF, we had built OWL, then we had queries, SPARQL queries, and then SHACL validations, and also we had used Apache Gina for running multiple SHACL queries, SPARQL queries. And in part 2, we built, we extended the existing ontology, healthcare ontology that we had built using the Protégé tool. We extended that to make it as a knowledge graph assistant, where we had built few APIs where we had at first we had ingested the ontology that we had built into the property graph database Neo4j. So we performed various kinds of transformations there, and then once we built there, we validated all the data, and then we built few APIs, and then we converted those into natural language to SPARQL and natural language to Cypher, and then SPARQL to Cypher queries. So when the Streamlit UI app, there the user is putting some kind of natural language queries. Then in the backend, some kind of SPARQL queries were getting generated, some kinds of cipher queries were getting generated, and those queries getting executed in the respective database. That is the Neo4j in the cipher and existing ontology for SPARQL queries. And after validations, the execution results were getting displayed in the Streamlit UI app in the natural language format. So this was a simple traditional chatbot. So we named this as a knowledge graph assistant. Now, next, this part again we extended to make it as enterprise multi-agent AI systems. Even though I will repeat during this course, I will repeat again and again, even though this course I have named for that is based upon the healthcare ontology as part in order to demonstrate you how to build ontology. So I have taken the healthcare ontology, but this whatever is the architectural principles I have followed that can be applied across various domains and the various industries. So let's start without making any delay. So I'm really excited to have you here. Artificial intelligence is evolving at an incredible pace. Just a couple of years ago, most AI applications were simple chatbots that answered user queries. But today, organizations expect AI systems to perform much more than conversations. They expect AI to analyze complex enterprise data, collaborate across multiple systems, reason over knowledge, and plan multiple workflows. Invoke external tools and learns from previous interactions and continuously improve their decisions. In other words, we are moving from conversational AI to intelligent enterprise AI systems. This course is all about understanding how those modern enterprise AI systems are designed. One of the biggest misconceptions today is that connecting a large language model with a retrieval augmented generation pipeline is enough to build an enterprise AI applications. It is not. A traditional chatbot is fundamentally stateless, and every request is largely independent, and it receives a prompt, generates a response, and the interaction ends there. Even if conversational history is provided, it has very limited awareness of long-term objectives, enterprise workflows, governance policies, business processes, or organizational knowledge. But enterprise systems demand much more. They need AI that can maintain long-term context, remember previous interactions, understand organizational knowledge, collaborate with specialized agents, make decisions, validate its own outputs, interact with enterprise tools, and continuously adapt based on new information. So this is exactly where stateful multi-agent AI systems come into the picture. The stateful AI system maintains a continuous evolving state throughout the execution of a task. And that state may include the current objective, conversation history, retrieval knowledge, intermediate reasoning, execution plans, tool outputs, memory, user preferences, workflow status, governance decision, and even confidence across the confidence scores produced during reasoning. So instead of solving a single prompt, the AI continuously updates its understanding as new information becomes available. This persistent state enables the AI to perform long-running, complex workflows that would be extremely difficult for a traditional chatbot. Throughout this course, we will see that an enterprise AI platform is much more than an LLM. It consists of many specialized components working together. You will learn how multiple AI agents collaborate, where one agent retrieves knowledge, another performs reasoning, another plans future actions, another validates outputs, another invokes enterprise tools, and another ensures governance and compliance. This collaborative architecture is what makes multi-agent AI significantly more powerful than a single chatbot. So real-world AI systems cannot rely only on information stored inside a language model. They must interact with external systems. For example, an AI assistant may retrieve patient records from an electronic health record systems, execute SQL queries on operational database, search an enterprise knowledge graph, invoke external APIs, analyze medical images, access document repositories, or trigger enterprise workflows. The AI becomes an intelligent orchestrator that knows when to use the right tool and how to combine the results into meaningful decisions. So memory is another critical capability here. So we'll explore different forms of memory, including the short-term memory, conversational memory, long-term organizational memory, semantic memory represented through enterprise knowledge graphs. So what happens now when we are doing conversations with the systems? Multi-turn conversation. So each conversation gets stored inside the knowledge graph. Episodic memory for previous interactions and workflow memory that enables AI systems to resume complex processes even after interruptions. So these capabilities transform AI from a reactive assistant into an intelligent enterprise collaborators. So another major theme of this course is the knowledge representation. Large language models are excellent at generating language, but enterprise organizations possess enormous amounts of structured knowledge that cannot simply be placed inside prompts. So we will learn how to organize healthcare knowledge using ontologies, taxonomies, semantic relationships, medical terminologies, and enterprise knowledge graphs. Once knowledge is represented properly, then AI systems can perform explainable reasoning instead of simply generating statistically probable text. We'll explore retrieval augment generation, that is GraphRag, semantic retrieval, hybrid search, graph traversal, and multi-hop reasoning to understand how enterprise AI retrieves accurate and explainable information from massive knowledge repositories. Building an enterprise platform that is secure, scalable, observable, explainable, governed, and maintainable is a completely different challenge. We will discuss logging, monitoring, evaluation, testing strategies, governance, compliance, explainability, security versioning, deployment architectures, and operational best practices that organizations expect from enterprise AI systems. Although our domain throughout this course is healthcare, the architectural principles we will learn are broadly applicable across many industries. The concepts of stateful AI, multi-agent collaboration, enterprise orchestration, knowledge graphs, GraphRag, event-driven systems, semantic interoperability, governance, and AI engineering can be applied to finance, manufacturing, retail, telecommunications, insurance, logistics, and many other enterprise domains. Healthcare simply provides one of the richest and most challenging environments for demonstrating these concepts. By the end of this course, we won't just understand how to build an AI chatbot, we will understand how to design an intelligent enterprise AI platform capable of reasoning over enterprise knowledge, maintaining long-term state, collaboratingly through multiple specialized AI agents, integrating with enterprise systems, and supporting complex business workflows in a scalable and production-ready environment. So whether we are an AI engineer, software architect, solution architect, machine learning engineer, data engineer, healthcare technology professional, or someone preparing for the next generation of enterprise AI systems, the course will provide both the conceptual foundation and the architectural thinking required to build the modern AI platforms. So thank you for joining me on this journey. Let's get started and build the next generation of enterprise multi-agent AI systems together. Thank you.